Hey, how's it
Hey,
going?
good.
Thank you so much for joining me. I would love to hear a little bit about how you got interested in phylogenetics to begin with.
Yeah, so it was actually not planned. I come from math. I did math in college. I've always liked math. I knew I was going to do something related to math in my career. And when I started the PhD in statistics, my original intention was to go into something financial.
Oh,
So,
wow.
and then, and that was what I had thought for since forever, or very theoretical, like statistical theory, but more from the probability theory
Hmm.
side. That was what
Yeah.
I thought was going to be my path. But then I heard one talk that changed everything, and this was a seminar talk by Brett Largett. I don't know if you
Hmm.
met him. He and well, he's amazing, and he does a lot of phylogenetic stuff, obviously.
Yeah.
And he gave a talk in one of my classes. He was an invited guest, and he talked about just it was not that complicated. He was just talking about like models of evolution, the different models, the Jukes Cantor, and I don't even remember what specifically he talked about. But for me, it was so interesting
Wow.
to think that probability could be used to answer
Hmm.
some questions in biology, and that completely changed my perspective. And I really wanted to learn more. So that's when I became really interested in evolutionary biology.
So I guess you probably had some coding experience then before your biology experience.
Oh, actually, yes, for sure. I did, like I said, I did math in college, and I took a lot of programming classes. Well, not a lot, but some programming classes.
Hmm.
And I, yeah, no, biology, the last biology class that I took was high school.
Uh-huh.
So,
Wow.
yeah,
Wow.
yes, I've had biology is really complicated. I've had to learn a
Yeah.
lot as I go. Programming
Yeah.
too, but I feel like I had a more stronger foundation on programming than I did in
Yeah.
biology. So, yeah.
Yeah. I mean, it's amazing how many fantastic resources there are now for picking up programming technique and stuff. But I think that in the enthusiasm to embrace computational approaches, there's some more formal aspects of the field that actually haven't really fully penetrated biology and are starting to now, which is really exciting as we rediscover some of the challenges that have been addressed elsewhere, like some real fundamentals of software engineering, for example, like, how do you write robust code, which then also tends to be the most easily extended and stuff like that. And then also we see all these industry tools like version control with Git and
Mhm.
everything coming in, and it's really fun now. Yeah, so my computational experience and math experience also precedes my interest in evolutionary biology. And for a while, I was wondering, if I wanted to be an engineer. I worked in
Mhm.
Silicon Valley for a little while, and I
Oh,
liked that, but
yeah.
um, I knew I wanted to get outside and ask questions about the natural world. And I thought I was leaving all that when I went to biology. I was like, okay, I'm going to forsake and leave behind me, this computational stuff I love. And then I went to biology. And then, of course, it's like, what was I thinking? Like
Yeah.
we get to do the computation, we get to do the math. I've been hearing a lot about Julia for a few years, and I haven't used it in any of my own projects. And I started playing with it a little bit today when I was going through your code, and there's quite a bit I like about it. But as an experienced Julia programmer, like what drew you to it?
Yeah, so I started doing Julia and doing my PhD, and I think I did not mention I did my PhD in statistics with Cécile here at
Uh-huh.
UW-Madison,
Right.
where I still am. And so when you're doing a PhD in statistics, you can be purely theoretical and don't care about computational at all. But we did not want that. We wanted to implement the theory, the pseudo-likelihood
Mm-hmm.
theory that we were developing, because ultimately we wanted biologists to use the tool to estimate phylogenetic networks. So when we started to think, okay, how do we implement this? We wanted something that it was easy to use, like it was more. It seems like you were saying, like computer science is starting to get more and more into biology. And I see a lot of more biologists that are comfortable with R, for example, than many years ago. So they use it more frequently. So we wanted something like that, like R, that it is simple, that you just install a package and then you have a tutorial and then you get started. You don't need to compile, you don't need to do all these different steps. So, but R can be very slow and very inefficient. So basically our only whole idea was to do the hardcore computation on C++, and then having an R package as a wrapper that would just run the C++ code. That's what a lot of people end up doing, to have their R packages. But luckily for us, there is this professor here in statistics. Well, he's retired now, Douglas Bates. He is one of the core developers of LME4, for example, for R, that does a lot of the linear models. And he is getting a lot into Julia. And he was back then. This is 2014, 2013. And he really got us excited about Julia. So he started, Julia was just had like a year, 2 years old when we started coding in Julia.
Wow, that's
so it
amazing.
was really, really new.
Yeah.
And so he told us precisely the goal of Julia is to avoid the two language problem, where you code parts in C++ and then you code parts in R. Right? In Julia, you have a high level language that is easy to run and easy to learn as R, but it's fast and efficient as C++. So you can write everything in Julia. That's the whole point, that you don't need to go through different languages. So we were convinced. Sorry, go ahead.
Oh no, that's fantastic. And it is kind of amazing when you get into source code, when you realize how many languages are being used. Like, for example, lots of R packages are using Fortran on the back for a lot of critical things. And of course, C++, as you mentioned. So so that's really nice. One of the biggest pains with the two language issue is it just adds this extra step when you're thinking like, okay, does this live on the C++ side of the divide, or does it live on the R side? And then sometimes you make these design decisions that have lasting consequences that are really hard to sort out. So that's so nice to just not even have that fence down the middle of your project to begin with.
Yes, exactly. And one other thing, sorry to interrupt you, is that it also makes it very easy for others to collaborate on your code. So if you ever try to, I don't know, add a functionality to an R package where the code really C++ is much harder to track that code down in CRUD, like, okay, where is it? What is going on? And Julia, everything's on GitHub. So we have, for example, in our package in PhyloNetworks, we have different contributors that are able to add more functionalities precisely because all the code is out in the open and it's very easy to find.
Yeah, that's great. But that's pretty bold, jumping on a language that early in its development cycle. So, but it looks like it was a great move. I mean, Julia, of course, has become very popular for a wide number of problems. So.
I do not reject it. I regret it. I mean, I do not regret it.
I was hoping that we could actually take a closer look at SNaQ. Your fantastic package for simultaneously looking not only at phylogenies, but also at hybridization events and incomplete lineage sorting, which is this exciting trend that we're seeing where it used to be there was a purpose-built package for every single task, which meant that you couldn't borrow information across the data when you're, inferring multiple processes and things. So, maybe one day there'll be one tool that just does everything. But in the meantime, it's really fun to see more and more processes explicitly accounted for with model-based approaches. So if you could just say a few words about what SNaQ is for, what goes into SNaQ, and what comes out of SNaQ.
Yes. So SNaQ, just like you mentioned, is it's an estimation process that maybe it's easier if I tell you what you get at the end. So it's an estimation process that you get a phylogenetic network, and a phylogenetic network is just an extension of a tree, where in a tree we have the speciation history of events of the organisms under study. A network has added reticulation events, we call them reticulation events or hybridization events, where we have joining of branches, creating either new hybrids or some gene flow going from one population to another. And this is at the group level. So it's if people are already familiar with recombination graphs, for example, that's at the gene level. This is at the population level. So we have the idea is that we have gene trees within the branches of this network. And just like you said, the characteristic of a SNaQ is that it accounts for both incomplete lineage sorting for the variability of the gene trees and hybridization. So we are modeling both sources of discordance in a unifying framework. And the way that we do this, this estimation process is via pseudo-likelihood function. So that's and we can get into more details about that later on when we talk about the pseudo-likelihood, but it's more scalable, as its name suggested. We're breaking up the computation of the likelihood into pieces, which is it allows the estimation to be more scalable than with the true likelihood.
Yeah, absolutely. I definitely want to get into that because of course, there's always a whole set of trade-offs. So which processes do you accommodate? How richly do you parameterize each of those? Speed, engineering costs, all these things. And in order to gain in one place, you have to make sacrifices somewhere else. And I think that often we just want everything to be perfect, and we like lose a lot by not being willing to make some of these trade-offs. So it's really fascinating to see the progress you've been able to make on some problems that people have even thought is non-identifiable. You know, you can't simultaneously do these things by moving, for example, from the likelihood to the pseudo likelihood. Should we take a look at some source code?
Of course, yes.
Okay.
The code will be found here in this source folder, like we are in this PhyloNetworks GitHub repository, has all the code. And then if you want to look at the specific, where the actual code is, that's in the source I'm clicking.
I'm actually fascinated by how people store trees in their program. This is this like crazy thing that you would think it's just one problem to solve once, that you know everyone does the same thing, but there's fascinating variation, and I was really excited to get into your code and see how you're doing it. So if we could take a look at the types file and take a look at what the primitives are that you build up into a tree.
For people who are familiar with object-oriented programming, this is where you define your classes. And it doesn't have to be called types, but that's what they are called in Julia. They're called types, so that's why I named it that way. And yes, is there any specific thing that you want me to go over?
So it's interesting. When I think about tree representation, some data models tend to be more edge focused, where you're defining your edges. Others are more node focused, where you think of the net nodes as the primary and then you connect them up. You have this really interesting approach where you have these abstract nodes, which, do you pronounce them anodes? Because that would be great. So
yes. Actually, I think this is the very first time that I've had to say it out loud.
See, that's why it's so fun to look at code. So
the A node.
Okay. So these A nodes, you have the abstract nodes that you then use to build a edge, but then the actual nodes in the tree inherit from the A nodes, but are defined in terms of the edges. So you go nodes, edges, nodes.
Yes, and we had to make that decision because just like you say, like this definition is circular. Like we needed the node to define the edge, because if you look at the edge object has two nodes attached to the edge. So, and again, just going back, these are classes. So we have the node class, we have the edge class. The edge is connected to two nodes. So when we are defining the edge needs to know about the node class. But when we define the node is connected to three edges because we have this binary graph. So the node also needs to know about the edge class. So which one you defined first was troublesome. So we came up, the solution that we found was to create this abstract type that is the node object first. Then the edge will refer to this abstract type that we have not specified, but the edge node that it exists, the abstract type, and then the specific node, which is a subtype of abstract node for
Yeah.
the specific node. But yeah.
Okay, that's great. That makes a lot of sense. And so then a tree is a vector of edges, and each edge points to some nodes. Or I guess also the vector of nodes also lives in the tree object. Is that the case?
Yes, yes. So we actually call it a network object because it
Of
could be a
course,
tree or
yeah,
it could be a
yeah,
network. But yes, you're
yeah.
right. And it does have an array of nodes and an array of edges.
Okay.
Aside from many other attributes that were used within the optimization, the internal optimization.
Yeah.
So yeah.
Okay, that's great. This is extremely well documented code, which is so nice.
Oh, thank you.
So that's great. And I was wondering, some of the headers that almost look like those could also be parsed out into documentation. Is that the case? Are there auto documenters?
Yes, exactly. That's these quotes, 3 quotes. That's exactly when the Julia documentation for the package is created. It parses out all of these headers into the documentation that I can also show it later. I'm gonna open it up here. In case you're interested, there is this documentation button in the package, and then here is where you will get those parsed chunks of text.
For working with networks and questions related to phylogenetics, were you starting from scratch in Julia, or were there existing libraries to handle primitive types that
No, we started from scratch. We had to create all the objects, all the libraries, all the functions, everything. There was nothing. So we had to create everything from scratch. Yes, yes.
Having looked at how you're representing the trees, I would just love to go through the code in whatever order makes logical sense to you. So like, where does the input come in? And then what are the primary math and stat steps that are being implemented through to the output?
Then start by showing here, because this is where the input, so in the wiki tab, this is where the input, we describe what type of input is used in SNaQ.
Yeah, I think it's in the SNaQ tab itself after the introduction. So you clone the Git repo.
Oh, you're right. You're totally right. Okay, so SNaQ takes two different types of input for the estimation of the network. So we can either use a list of unrooted gene trees that were estimated previously via whatever method the user likes. I put here RaxML is one option. It could be Mr. Bayes, SNaQ tree. There are different tree estimation methods that go from the sequences into the gene trees. And we highlight unrooted because other network methods will require you to root the gene trees, and SNaQ doesn't need that. Alternatively, you could use a table of concordance factors as input. And these concordance factors can be estimated from software like Bucky, where, again, you always first need to estimate gene trees, but in this first step, you have to do it with Mr. Bayes, so that you don't have a point estimate to the gene tree, you have a posterior distribution for each of the genes. And then Bucky, what it does, it takes these posterior distributions and it clusters the gene trees to account for gene tree estimation error. So at the end of the pipeline, you get a table of concordance factors that I think we have an example here. It's a table that is, if you have 10 species in your data set, you would have all the different subsets of 4 species. So for example, here, this is simulated data, so not real species. So it's a species 6215. So this is one subset of 4 if we had 10. And each row in this table corresponds a subset of 4 species.
And are those edge lengths? Okay.
These are not edge lengths. These are the concordance factors.
Oh, they're
so what that
right,
means,
of course.
Is if I have there are 3 possible unrooted resolutions. So either 1 or 2 are together, 3 or 2 and 1 and 3, or 1 and 4 are together. So are the 3 options. And then each of these options is supported or not by your sample of gene trees. So you observe this in certain proportions. And that is what is represented in each row. So it's the 4 taxon subset and the 3 values for the concordance factors for the 3 different resolutions.
Got it. And so if you're importing like a RaxML tree internally in SNaQ, you're creating this concordance factor table, right? Okay, so everything goes through the concordance factors. It's just whether you import them directly or calculate them from trees.
Exactly.
Okay.
And the difference is if you import them directly, if you put the gene trees and we calculate the concordance factors internally, we are not accounting for estimation errors. So we are using the gene trees as perfectly known and getting the concordance factors. Whereas if you use Bucky in the pipeline because of that clustering step, you account for estimation errors.
Great.
Yes.
Great.
Yes.
So in general, would you recommend using Bucky upstream of SNaQ then?
Exactly. Yes.
Okay.
Yes. That's the approach that we recommend. Although if people have already estimated their gene trees, they can use them directly as input. Yeah.
Great. Okay.
Yes.
That's really nice flexibility. Okay.
Yeah. Okay. So now that we've seen the two options, so this function read trees to concordance factors, you will give them the file that has your list 1 row per tree, and this function will read this table. And well, one thing that you will see is that it has a lot of arguments depending on whether, because so by default you will create all different possible 4 taxon subsets. But maybe if you have 100 species, then you have 100 choose 4, I don't even know what that is,
it's big
subsets.
Yeah.
And maybe you don't want all of them, so you want a shorter. So we are giving the option for people to choose the quartets that they want to include, or if they want to choose a sample that is randomly chosen, which size. So anyway, this is just to allow flexibility. If people want to use all the quartets, then they don't need to care about all these different options. Yeah. And then, so you will see, so because this was one of the errors. So the thing with this code is that when you start coding it as a student, you don't have the best names for things. So you will see my file was really called read input data.
Awesome.
Which was of course not was precise enough because we have different types of input data anyway. So eventually, so the read trees to this read input data, which is the one that is actually doing the work. So maybe we need to look for this one. So
sorry, I hadn't seen this in Julia before. So you can overload the functions. You can define multiple sets of arguments.
Yes.
Okay, great.
Yes, exactly. And the other thing is that we are defining different versions of the same function depending on what arguments we are making default or not. This was not the best in retrospect. We could have set some of those. There's a way to set an argument to give it a default value,
right,
instead of creating new functions. But anyway, this was probably one of the first functions that we had. And as I told you, I mean, it's not an excuse, but as we were doing the code, so there were decisions that we made at the beginning that are definitely not
as
the
always.
best decisions.
Oh no, well, it's interesting because that first approach is very C-like, and then the second approach of defining defaults is very Python-like. So it shows that it bends both ways.
It is, yes. And I guess without getting into too much details, this is the function, the calculate observed concordance factors that is reading this list of trees and calculating the concordance factors later on. Because like you said, at the end of the day, that's what we need, the concordance factors table. Yeah.
Great.
Yeah, so I don't know if it would be interesting to see this function.
Let's take a look.
Or no. Oh, and one thing actually that I did not mention is we have another data type. Oh, and actually this is important data type. So let me open this one again. So we created this object type data CF, which is it holds the data, and also holds some of the, at the end of the day, the pseudo likelihood is comparing the observed concordance factors with the expected concordance factors. So what you would expect from the model versus what you really observe. And we created this object that is holding both the observed concordance factors and the expected concordance factors, so that we can iterate through them and calculate the pseudo likelihood.
Great.
So in this object, we have a list that is giving us the the concordance factors. Yeah, so we have a list of quartets, and each quartet has its own observed concordance factors or expected concordance factors. So you will see, I mean, if you look into these types, we have a lot of different objects that we had to create.
Yeah.
So yeah, anyway, let's look back at the, sorry, where are we? Oh, here it is. We wanted to calculate observed concordance. So I remember because this is the object that we need to calculate the observed concordance factors, because we are reading the tables and we're filling out this data CF object. And one thing that I want to mention is that you will see Julia functions that end in exclamation sign.
I was just going to ask about that.
Yeah. So these are, it's just like, I don't know, like by convention, that if the function changes the argument internally, then it has an exclamation sign. And that is something that it's different from R, because in R, when you pass an argument, you really pass a copy of the argument. So if you're passing, for example, a gigantic matrix, you have to copy it. And there might be ways not to do that, but I don't know how. But in Julia, you are passing the object, and you can modify it internally. So that's, you're not creating a copy for that. Yeah.
So the names are all really pointers, and you're passing by reference.
Yep. Exactly.
Okay.
Yes. And so let's see. And yeah. So yeah. You will see functions inside functions, because we had different names at one point. And actually, so this was a function that I had coded as a student before, and it was so slow and inefficient, and people would have to wait 30 minutes for the data just to be uploaded into SNaQ. It was a nightmare. So then Cécile created her own version that was a lot more efficient.
Okay.
And this is the one that we are using now. And so this is I actually have not seen many of the code, but basically the high level description of this is that you first get the list of all the quartets, all the subsets of 4. And then for each of them, for example, you have taxa 1, 2, 3, 4. You iterate through your gene trees so that you see what resolution. If I only extract the 1, 2, 3, 4 subtree, what resolution do I get? And then you count. So you are counting. If you have the 1, 2 together, you count 1 in that, or if you have 1, 3 together. So you are always iterating through the gene tree. So it's very slow. I mean, it's not. It will take time. If you have 100 species and you have your list of million of quartets, then of course this is going to take time.
Yeah, absolutely. Yeah. Okay.
So yeah, so here you see you are iterating through the trees that we had. So first we're iterating over the quartets. So that's all of our subsets of quartets. And then here we are adding whether we see 1, 2 together, or 1, 3, or 1, 4, which of the 3 possible resolutions. We're setting them all to 0, and then when we're iterating over the trees, we are just adding if we see the first resolution, second resolution, third resolution. We're just counting. That. And at the end, we just divide. The observed concordance factors are the 3 different resolutions, 1, 2, 1, 3, 1, 4, divided by how many times we found this resolution. And one thing that, I mean, I think I remember you mentioned something about missing data. So one important point at here is that we don't need all the gene trees to have exactly like all the taxa. Like you could have gene trees that have missing taxa. You can have, it's just a matter that if you don't find those 4 taxa, you will just ignore that gene tree.
Okay, great.
but it won't crash. That's the only thing. Like it allows, if you have missingness on your gene trees, then that's fine. You just won't. You will have yeah, exactly. Like you will perhaps be biased. Your concordance factors might be biased depending on the missingness patterns that you have. But yeah.
Okay.
Yes. Okay.
Great.
Cool. So let's see, where were we? We're still reading in the data.
Well, let's see. Maybe, so let's say we have all the concordance factors.
Yes.
At this point, what comes next?
Yes. So what comes next is that we need to search the space of networks, basically. And we have to start somewhere. And we ask the user to also give us that. So if you will see, we need a starting topology to run SNaQ. And this is just, we don't choose a place randomly to start the optimization.
Yeah.
We want to find, and this could be a tree that you get from a fast method like Quartet Mascot or Astral. Actually, Quartet Mascot uses the same table of concordance factors. So if you have it already, you can run Quartet Mascot and get a starting tree really fast.
And the starting tree, that's fully resolved, so it's strictly bifurcating?
I think, yes, it is strictly bifurcating. Yeah.
Okay.
But to be honest, I don't know if there is any, I mean, it could be unresolved and the program would probably not complain. But one of the things is that we have not fully tested it under unresolved scenarios.
Yeah.
So it could break, but there's nothing in theory that it's that requires it to be fully bifurcating. It could just be a computational thing that perhaps the code will break, but there is it shouldn't.
Okay.
That's what I mean.
All
like,
right.
It shouldn't break.
Great.
Yeah. So anyway, so we're gonna start somewhere. That's the first tree, and the method, what it does is it calculates the pseudo likelihood of that starting tree. So I'm gonna tell you the high level optimization. So you start somewhere, you evaluate the pseudo likelihood. Well, actually, you don't evaluate. You optimize the branch lengths to maximize the pseudo likelihood, and then you propose a new tree or network based on certain network moves that I can tell you later. But you propose a different one. Sorry, go ahead, Casey.
I was gonna say, so that very first evaluation, if you have a strictly bifurcating tree, so is H 0 for that very first pseudo likelihood?
Yes.
Okay.
Yes.
And you've specified H, where H is the number of hybridization events that you're going to go to. So you then add the hybridization events like sequentially, or maybe you're getting to that.
Yes, and that it depends on the moves. So when we go from one topology to another topology, there are 5 different types of moves that we choose randomly.
Great.
One move is add hybridization. So we add hybridization, and this has to check obviously that you have not exceeded the limit that we set. You're right.
Okay.
So one of the arguments in SNaQ, we have to set the maximum number of hybridization.
Oh, so that's a maximum. I thought it was, okay. Okay, great.
That's a maximum, but to be honest, because we don't impose any penalties, you will most likely end up with that number.
Bumping up, yeah.
Exactly.
Okay.
Yes. But it is a maximum, so you could potentially end up with a network with fewer hybridization events than the one you set.
Okay.
And yeah.
Okay, so 5 moves. Great.
5 moves. Adding hybridization and changing the direction of the hybrid. So if we pointing this way, we flip it so that it points the other way. That hybridization arrow.
Oh, because it's not, right, of course, it's not 1 minus gamma. You could have 2 hybridization events between the same edges in the tree, even with different gammas, or except, yeah, that would create a higher order cycle. Okay.
Yes. So in theory, you could, but like for any network, you could have different hybridization events between the same edges. In SNaQ, we don't allow that to happen because of the level 1 restriction.
Right.
Yeah.
Okay. Yeah. And so just to clarify, so the level 1 restriction is so that each edge can only be part of a single cycle.
Exactly.
Okay.
Exactly. Yes.
And why does it get so much harder if edges can be parts of multiple cycles?
So for us, so first of all, the space of networks is bigger. So right now we're traversing the space of networks to find the one that maximizes the pseudo likelihood. So we are restricting it to the level 1. So it's a smaller space that we have to search. If we allow for any level, there are different categories of networks. So if we allow a broader class, then of course this space is bigger. So we have a traversal large. So the optimization could be or would be slower. That's on the computational side. But also on the theoretical side, we could prove identifiability for the level 1 networks, but not yet for a broader class of networks. So it could be the case that 2 networks that are different, they have the exact same pseudo likelihood score.
Gotcha.
So that would be they're not identifiable. So so to be honest, that's what I'm working on right now. I'm trying to extend SNaQ to a broader class of networks, but that involves some study of identifiability. And that's where we are struggling. Yeah.
Okay. All right. I feel like I keep distracting you. So we got
No, that's great. It's great. It's great that you have questions. That's great. So yeah, the 5 moves. So we have adding hybridization, flipping or changing the direction of the hybrid edge. We have the move origin of move target of the hybridization. So if you imagine, I wish we had like a whiteboard, but if you have a arrow that's pointing, then you can change this origin from this edge to another edge. So it's still pointing at the same target edge, but you're moving where it starts, where it originates. So that's move origin. And we also have move target, where you fix where it's coming from, but you change to a different place where the arrow is pointing, a different edge.
Yes. Okay.
And then the last move is not really, the first 4 moves have to do with the hybridization event. And then the last move is just an NNI move for the 3 parts.
Okay.
So we would pick an edge. And for any of these moves, so first we would pick a move at random, and then we would pick the edges that are involved for the move.
Okay.
So yeah. So anyway, so that's how we would go from one topology to another, picking randomly one of these moves.
Okay.
And then at any new proposed topology, we need to optimize the pseudo likelihood to find this score.
And do you have to optimize branch lengths as part of that?
Yes.
Okay.
So we optimize branch lengths and we optimize the gamma parameters that are the inheritance probabilities.
Right.
Yeah.
Okay.
Yeah.
One question I had has to do with this interaction between H and the gamma value, because you could almost think of like a very large number of H events that have very low gamma values each, or like approaching 0. So it's only like the non-zero one. So like how does H and gamma interact in practice? Does it end up like when it's above a certain threshold, then it counts and you see it as a hybridization?
Yes, actually, I'm so glad that you asked this question. And this is probably the very first time that I've talked about this. And this is a really exciting part of the code, because we do, when we optimize a gamma that is very close to 0, we don't put it, basically.
Okay.
So we do have a threshold for that gamma, which I don't remember. It's probably something that you can set as a user. And right now we're very lenient in a way, like we don't remove hybridizations unless they're really, really, really close to 0.
Yeah.
But this is something that could be changed, because you're right. Like you can end up with too many hybridization events. They all have very small gamma. So we do make that change after we optimize for the gamma. We check if we have a gamma that is very close to 0. And to be honest, we try to keep it there. So first we do moves around this gamma close to 0 edge. So we change the origin or the target, we flip it and re-optimize just to see if any of those changes give us a higher gamma. And if we fail, if it's always estimated to be close to 0, we drop it.
Okay.
Yeah.
And if you were to say, put in a tree that had a simulated tree that had no hybridization events, but you told it, you let H be like 4 or something, would it tend to just estimate very low gammas then?
We have not. This is something that we do want to do. We should do this simulation study. I suspect that's what would happen. It will add these hybridization events with low gamma, but I have not done the simulation study, so I wouldn't know for sure. But yeah, this is what I would suspect. Yeah.
Okay, and if that's the case, it would be a nice way to tune H.
Yes.
You could just keep increasing H until the magnitudes of gamma start to
Yes.
fall off. So,
yes.
okay.
Yes. Maybe what we want to see, so this pseudo likelihood is where the pseudo likelihood is being computed.
Yeah, let's check that out.
And it is really a bit messy. So we'll see. Let me see if I can find. Because so the way this, I think I told you that before that the pseudo likelihood is considering both the observed concordance factors and the expected concordance factors. So the key point in the pseudo likelihood is how do I calculate the expected concordance factors? And the expected concordance factors, they come from the proposed network that we have. We need to extract the quartet, and actually, I think that might be easier to see in the paper. Yeah, so we have functions, for example, that have extract quartet, where we give the network as the input, and then here we're giving the whole list of quartets that we want to extract.
Okay.
So we created this quartet network type that will extract just that subnetwork that has just 4 leaves. And then for each of these quartets, what we now have to do is calculate the true likelihood on the quartet. Sorry if I'm making it easy.
No, it's just amazing. Like in my conversation with Joe, one thing that really surprised me was his emphasis on bookkeeping. I mean, I knew how important it was, but it's fascinating to look through your code and see how much, when you're calculating a likelihood or a pseudo likelihood, is this bookkeeping as you move through the tree.
Yes, exactly. And I, to be honest, I don't think we do it as good a job as probably Joe's code is doing, because we are redoing calculations that we might not need sometimes. But we try not to. So because when you're moving from one network to another network, because we're doing these local moves, most of the network remains the same. So we don't really need to recalculate the likelihood for many quartets, which at right now we are kind of like in the middle. We don't recalculate everything, but we do recalculate somewhat that we shouldn't. We're not being super smart with this computation. But you're right. I mean, smart bookkeeping is the way to improve code.
It is, but it takes
repetitive tasks.
Yeah, it takes a lot of human time to engineer the code that reduces the amount of computer time. So it's often appropriate to just redo it, as you say, because it's a lot easier to maintain. It just depends.
It's like a balance, like you said. It's always a balance. Like you can spend a lot more time just making efficient, but then maybe you don't have that time, so you make a slightly less optimal version of your code.
Yep, absolutely. Okay.
Yeah, this is what I was trying to find. So once you've extracted networks, and actually let me see if I can make this one bigger. Yeah, okay. It turns out that there are different types. We call them different types of quartet networks, depending on where the hybridization event is placed. So if it is pointing here, for example, at the internal branch, or is it between these external branches that lead to specific leaves, or if it's going from one leaf to another opposite leaf, the hybridization. So these orange arrows are the hybridization events.
Gotcha.
Yes.
That network 4 is fascinating that you allow that.
Yeah.
A split and then a remerging. Okay.
Yes.
Yeah.
Yes. And so each of these quartet networks have different, these are the formulas for the expected concordance factors, the true concordance factors, we call them for the network. So our code basically, if we go back to the code, has this function that says identify quartet, which is just basically just telling you which of these quartet I'm looking at.
Okay.
So there are 5 types of quartets, because once that you identify, oh, I'm this network 1, then we know the formulas. We know which are the formulas that we can calculate.
Gotcha.
So the code really needs to identify
and
them.
Just to clarify, when you have a hybridization event, the exact position on the edge matters, doesn't it? So it introduces 2 additional edge length parameters that have to be
Yes.
accounted for.
Yes, exactly.
Okay.
So for example, in this first case, you see it breaks the internal branch into T1 and T2, because where this node lies in this edge, it matters. Yes, yes, you're right.
Okay.
Yep. And these are all these branch lengths, they are all estimated in the process. So
Right.
we do get where is that position within the edge. Yeah. So
Right.
And I would say the main challenge is just, or for me at least, it was writing this function to identify what type of quartet it was, or when we extracted it from the network. Because once you know which quartet it is, then you know which are the formulas. Here, for example, we have some of the formulas.
Yeah, that's exactly what I was going to ask, is
Some of the
where's
cases.
that math? Okay, excellent.
Yeah. Yes. So the math is in, so there are different places, but one of them is for example this quartet type 5.
Yeah.
This is the one of them. And,
yeah.
So.
And when you were writing this code, like, does Julia have profilers for looking at speed and things? Was that a big emphasis for you?
It does have it, but I think we didn't utilize it as much as we should have. Yeah. So I think for me, the main, because it was such a big task, just such a big implementation, that I was mostly interested to see if it was accurate or not. So we did absolutely. A lot of simulations. We simulated data on different networks, and we compared whether we got the correct network, at least from the simulations, because I was worried that it was not gonna, whether there was even a bug in my code that would never work, or maybe even if it was theoretically possible, perhaps the nature of the data could be noisy or messy, and then the signal of those hybridizations could be lost in real data. So anyway, I think I was more concerned with the accuracy and the applicability than the efficient code, having efficient code.
Absolutely. Yeah. And it's crazy because people are so used to this highly optimized software that, you know, big teams of people work on. But as like a grad student or something in your coding, you really have to decide what your priority is going to be. And if you're taking on a big project like this, you can't perfectly optimize every single step, or you will never finish. So.
Oh yeah, I will still be doing my PhD. Probably. Yeah. And you're right. I mean, yes. Sorry, go ahead, Casey.
Oh, I was just gonna say, the other thing you see sometimes is premature optimization, where, you know, if you spend too much optimizing right when you build things, then there's gonna be all these cases where you build something, then realize you don't need it, and you spent all this time optimizing the code. So it's good to circle back later.
The computer science sometimes say that first you want to make it efficient. Like your first priority should be that it works, or it does what you think it should do. Yeah. And then you worry about the efficiency, which we're still, I mean, I should say that there are still many places where we can improve this. We have done some work on improving it, but this is a really massive task, and it has been mostly been Cécile and me maintaining SNaQ specifically. So PhyloNetworks, which actually we never made the distinction, but PhyloNetworks is the Julia package that has many functions for networks, and SNaQ is one of those components within PhyloNetworks. And we were writing both at the same time, SNaQ and PhyloNetworks. And I saw in one of the questions that we discussed that what would if there was something that I would have done differently, and I would have split them. I think I would have been more clear about having PhyloNetworks to have all these different tools for networks, functions for networks, reading, writing, the network objects, and all that. And then SNaQ, a separate package that will have PhyloNetworks as a dependency, but we're just implementing SNaQ, because I think right now it's becoming a really big package that it's not ideal. It's not as modular as it should be.
Yeah, so, that is such a hard decision sometimes, like where does one project stop and where does one start? And then when is it worth it to pull out general code as its own separate package that you can then use elsewhere, because it also it comes at a cost of maintaining the two separate code bases.
Yes,
but
yes, of course.
Yeah.
Yes. Yeah.
So great.
So anyway, so basically that's I want to say that within this pseudo likelihood function, the main function is the one that and I didn't put much emphasis into this, but the identify quartet will just let us know which of these different options is it. And after you've done that, then we have functions for each of the types, and just the example that I had found before. So for the type 5, then these are the specific concordance factors formulas for that example. And there are many ifs in here, but
yeah.
Great.
Okay, that makes good sense. And
yes.
So then, so you're making those 5 types of proposals that you mentioned. You're optimizing the branch links under here. Yeah.
So SNaQ optimization puts all the pieces together. This is the function to propose a new topology. And here it will show the different moves that it will do and which is the function that does each of the moves. So add hybridization update is the one that will add hybridization. And then move origin, update, repeat. So the names there. So move origin will just move the origin edge of the hybridization update, hybridization edge. We have move target, change direction, and delete hybridization. This was not really one of the moves. So we implemented it as a move, but because of the nature, I mean, as you probably know, I mean, models that are more complex tend to have a higher likelihood or pseudo likelihood score. So a network with more hybridizations will tend to have a better pseudo likelihood score than one with fewer. So having a delete hybridization, because we are comparing the pseudo likelihood scores to accept a move, this move was never accepted. If we get rid of hybridization events, we will always or most of the times end up with a lower
reject it.
Score.
Yeah. And so if you are at the maximum H, do you always delete a hybridization before adding a hybridization? Is that
you would have
works?
to. Yeah, you would have to. Yeah, to delete a hybridization before you add a new one. Yeah, but most of the times what happens is you just end up moving the existing ones to different places.
Right.
You move them around.
Okay.
Yeah. And yes, and then there's the NNI move. And I think, I think the word, so one of the things, like I told you, we have to choose, if you have a network that has many hybridization events, you choose one randomly where you will do the moves that you will propose. So that's what this choose hybrid is doing. You're choosing randomly a hybrid node, and then you choose what type of move you want to do around this hybrid. You're choosing one move, depending on which is the move, you either do hybridization or origin, move origin, move target, change direction, delete hybridization or NNI, and the NNI move for 3 edges. Well, change direction is here.
Okay.
So change direction, you already have to tell them which is the node around which you want to do the change of the direction. And this is just, if you see, just a rearranging of nodes and edges. So we are identifying which are the hybrid edges that are connected to this move, which are the nodes, and then we are just it's not as simple as just flipping things, because we have to rewrite what's happening with the node and the edge objects.
Wow.
So, yeah, there's so many removing nodes, setting nodes. Yeah, I had forgotten how complex this was.
That's amazing. Yeah, I could just imagine you working it out with paper and pencil.
Yes,
exactly.
I had a lot of my handwritten notes, and and actually I use my iPad, so I even have some of those notes still, like me drawing where the node was supposed to be attached.
That's great.
And many things. Yeah.
I like the hand-drawn figures in the paper. Did you use the iPad for those
I use
too?
the iPad.
Yeah, that's great.
Yes. But anyway, ultimately, they're all just changes with the nodes and the edge. So it's just like you said at the beginning, like everything is building on this node and edge object. So all the moves are around these two types of objects. Yeah.
Yeah. Okay. That makes a lot of sense. And then what is your stopping criteria? When do you decide to stop making more moves?
Yeah, that is a great question. So we're keeping track of how much the pseudo likelihood is changing. And if we don't see many change, like if the changes are just incremental, there's a threshold over there, we just stop. And we also have we have like just in case this doesn't happen, and we're just like jumping around forever in the big gigantic space, we also have like a counter that we just allow a certain number of moves, successful moves, and then we stop. Yeah.
And was
so
that
different reasons? Yeah.
Was that threshold and that counter value, were those difficult to tune to get it to work reasonably, or did it work pretty well once you just tried to value
No,
it?
yeah, it was difficult, and actually to be honest, I think we still need to do a bit more tuning, because we were able to tune it for the networks we use in the paper. That the largest one has just 15 taxa. So all those tuning parameters work well with the size of network, but as people start to use bigger networks,
right,
we wouldn't know. But we try to be very conservative, like erring on the size of being very cautious. So we think that it will still work well, but it might be slower than it could be. Like there might be another tuning option that will speed up the optimization. But because we didn't test it, we have not done that. We did have one student working with us for a while, just playing with the tuning parameters and see whether they matter or not. And we kept as default the one that were still very accurate, but were faster. The optimization was faster.
Yeah, that's excellent. Yeah. Okay, that makes good sense.
People are interested in those tuning parameters. In the SNaQ optimization file, we have this nice table where we have the different tuning parameters they have to do with the pseudo likelihood, the absolute difference, the relative difference, number of failed attempts that we allow, the likelihood difference. This is for the pseudo likelihood. We call it likelihood, but it's really the pseudo likelihood. And then the latest step, the top row, that's what the results from what the student found with right here, Nanji's work. He did a lot of tests on comparing SNaQ with PhyloNet and different simulation studies. So these are the values of the tuning parameters that we're using, that, like I said, are chosen so that it's accurate, but also not relatively fast compared to other values. Yeah.
That's great. That's the exact kind of really critical thing that's often completely buried in the code.
Yeah.
And not at all explicit. Yeah. So
let me just point one last thing. So with SNaQ, with the output, we get the network in parenthetical format, with this like the extended NUIC format that you can input it in any other dendroscope or fig tree, or there are different ways to plot it. But we also have tools to plot in PhyloNetworks, so you can create your own plots within Julia, so you don't need to leave the interface. And there, all the information is in the documentation, and the wiki tab that I showed has a step-by-step tutorial for people that want to use the tool.
At this time, what number of taxa and what values of H are tractable for an analysis?
Yeah, this is a great question. So for us, when we did the paper, the largest network that we tried had 24 taxa and 5 hybridization events. Okay. And these in parallel, so we had to run it in parallel. Another thing that I did not mention is that we do the optimization on different runs, because we start somewhere and then you run until you converge, but you also want to start somewhere else and then run until you converge. You want to try different independent starting points. And by default, SNaQ will do 10 independent starting points. Okay. That you, of course, want to run in parallel, right? Yeah. You don't want to run one run after the other. It's going to take forever. So if you're running these in parallel, so for the case of the 24 taxa and 5 hybridization events, I think one run would take 6 days waiting time.
Okay.
So it was not automatic, but it was still doable, I guess. Like I think in phylogenetics, we're used to waiting a lot of time, so it doesn't scare us.
Yeah.
But that was the biggest one that we tested. I know of people that have used SNaQ on bigger networks, maybe 50. I wouldn't know how long that takes, but that's actually one of the things that I'm doing right now. I'm trying to test the limits of SNaQ, not just in terms of size, but also in terms of complexity of networks. Because of the level 1 assumption, I want to know what happens if the true network really is a lot more messier or has a lot more reticulation. Then what is that signal that we get at the end?
Right.
What is it that we estimate?
Yeah. One thing that I'm really interested in is how identifiable these different sources of gene tree, species tree incongruence are. Do you have a feeling for when ILS might look like hybridization or vice versa, or are the signatures so distinct that if those are the two processes, you're finding you can really pull them apart?
Yeah, I think it will depend a lot on what data we're using to distinguish it. Because, for example, one of the things with the quartets and the concordance factors is that you have, like I said, we have 3 different possible resolutions, and one will agree with the species tree. So one that we call the major resolution agrees with the species tree, and the 2 minors will conflict the species tree. But when there is ILS, the source of discordance, these 2 minors have equal frequencies.
Gotcha.
So they will be very distinct to hybridization, where you might have 2 that are competing because there's a hybrid. So we have 2 that are they're equally major and similar, and then one that is smaller. Or maybe all 3 have different, they're not 2 that are equal. So in this case, when you're using quartets, when you're using concordance factors, I think that the signal from ILS and hybridization could be distinct. But of course, I don't want to generalize. You can always distinguish it. But at least in theory, there is this difference in the frequencies. But I think that there could definitely be cases where they produce the same results. And one of the things that we found, for example, is that if we simulate data under a network, that we don't come from a network, but if we use a tree method like Astral or NJST, we end up estimating the wrong tree. So we found that the gene flow event really messes up with the signal from the gene trees, the gene tree frequencies. So the tree methods are not able to reconstruct. If they only assume ILS, then the gene flow is really messing up with the signal. So
because I wonder about that. Like, it's as people become more interested in ILS and they're using tools that can accommodate ILS, and you see these terms for how much ILS there is, I just always wonder how much that one term is soaking up hybridization, or the other process I think is at play in a lot of the data we work on is gene duplication and loss leading to gene tree, species tree incongruence.
Yes.
So is the duplication and loss like really fundamentally different to implement in this framework than ILS and hybridization are? Is that something you've looked at putting into SNaQ as well?
Well, yeah. So to be honest, I have not thought about putting it into SNaQ. It would definitely be another like we will need to model it explicitly. It will need to be another explicit inclusion in the model. And there are already methods that account for ILS, duplications, and hybridizations, by the way. But that's definitely where I think the field is going, is trying to incorporate more processes, as you said at the beginning. Personally, I don't see that as the next step for SNaQ. I want to be the next step, like I said, I want it to be to expand to broader classes of networks. That would be, I think I want to stay within the ILS gene flow framework for a bit before I start including more processes.
That's great.
But it's definitely, it's definitely important that we include more processes. Sure.
Yeah, that makes a lot of sense. I mean, there's always, 20 directions you could go. And a lot of the challenge is just staying focused to make clear progress on the primary one. So that's really great. So it is interesting that, you know, whenever anyone's writing any software of any sort, there's all these trade-offs. There's the engineering time, the investment in writing it, there's how efficiently it's going to run, how much precision there is, how much accuracy there is. And again, it's just really interesting that all these things, different tools often implicitly are making different trade-offs between these things. But I liked in the discussion of your paper how you really like spelled out what some of these axes of variation were and described, you know, exactly how you were positioning SNaQ on them.
No, and I do think that, yeah, I think you're right. I think there are different ways in which we can approach developing new methods for phylogenomics. And for me personally, I don't think there's a right or a wrong way, as long as, like you said, as we are explicit of this is what we're trying to do, right? Like these are the assumptions that we're making, and these are the choices that we're making with a method. And as long as you put it out there and just say, okay, this is the approach that I'm taking, and yeah. And interestingly, people have different priorities. Like there could be people, for example, I'm really interested in scalability, but without compromising identifiability. And there will be people that are saying like, no, I don't care if it's not scalable. I want it to be very precise, you know, like very accurate all the time, even if it's only for 3 species, right? So, and that's the beauty, I think, of the method, that there are many different tools that have different needs. So
yeah, I imagine it as this big hypervolume, you know, where there's, you know, approximation versus exact is one of the axes, and, you know, speed and everything.
It would be great to create
and all
this
the
figure,
tools
actually.
out there. Wouldn't it be fun?
It would be so fun to create this figure, actually. We should do it.
Yeah, let's do it.
Figure.
Wouldn't that be great? Yeah. And just to think about how the tools are positioned, and then you could even draw vectors as versions are added and the tool moves, you know, in the space. But, you know, magnitude of data set size and things would be in there. But I think too, when people come to phylogenetics, we have such a rich diversity of tools to draw on. People often land on one tool and then they get really frustrated with the tool because it's like not doing what they want to do. Like they think this process is super important. It's not in the tool. And it's often seen as like a bug or a deficiency in the tool. It's like, no, the tool just wasn't like built for that. You wouldn't be, you know, you shouldn't get upset if you like go buy milk and then you put it in the car instead of putting it in a refrigerator, and then the car doesn't keep the milk from spoiling. Like these are different tools. They're for different things. And so I think that'd be really fun to make that figure. I'd love to do that.
No, me too. Actually, yeah, we should definitely talk about this more. And I feel like there is like this disconnect that you mentioned, using the car as a fridge. I think there's fault on both sides. There's fault on the methods people side that are not very explicit about what they're assuming and what choices that they're making. And then obviously from the user side, that they are not using the right tool for the work that they want to. So
yeah, exactly. And there's really at least 3 or 4 layers of information about software. You have the code itself, you have the comments in the code, you have the information like in the repository about the code, and then you have like the paper, and sometimes stuff is duplicated, and so it
conflicting.
Can be, absolutely. Sometimes they completely drift apart. They just wander off in their own directions, which is so hard, which is why it's so nice now that documentation could be parsed directly from comments and things. Are you looking for students or postdocs or anything at this time?
Yes, I'm actively recruiting students, postdocs, I mean, people who are interested in developing methods in phylogenetics, but also, I should say, also collaborations. I like to collaborate with people if they have data sets that could be analyzed with SNaQ, or with, maybe not exactly with SNaQ, but there's something else that SNaQ might need to be added into SNaQ for certain data sets. Anyway, so yeah, I'm really looking forward to people that are either using SNaQ or they want to contribute to SNaQ. Let's just say it this way. So yeah.
Oh, wonderful. That's great.
Yeah.
Okay, cool. Sounds good. Well, thank you so much for joining me today. This was such a fun discussion. So
yeah, I had a lot of fun.
Yeah, it's great to learn more about your code and work. So okay, all right. Thanks so much. Okay, take care.
Much, Casey.
Bye. Thank you.